Okay, hey folks. Welcome to the first lecture of my mini course. I'm Lisa Piccirillo. This mini course is going to be about, well, it's called Knot Theory in Four Manifolds, and what it's going to be about is trying to solve hard four manifolds problems in a slightly easier setting, in a sort of relative setting where we have more tools. But that's not at all what this lecture is going to be about. When Andras and Naru and I were coordinating before this school, it was decided that somebody had to do some like hands-on dirty handle calculus in dimension 4, and it was decided that it was going to be me. And there's quite a lot of it to do. This lecture is going to do it. I'll tell you what the course is actually about at the beginning of the next lecture. So for now, without further discussion, let me jump right in about handle calculus in dimension 4. So don't freak out. This is the only slide that looks like this. I promise not to show you any more busy slides after this. This is just a slide where I tell you my conventions and remind you of stuff that you already know. So some conventions here at the top, they're all pretty standard. I'm going to use nu to denote a tubular neighborhood of a smooth submanifold. And maybe a notable one is that I can't seem to consistently decide whether I want Bn or Dn to be the unit ball, so I'm not going to pick. I'm just using both throughout the talk. So stuff you already know, because by the way, you have already watched Andras's first lecture and then Aru's first lecture before seeing this one. And if you haven't done that, you're going to pause and go do that and come back. So since you've already done that, here's some things you already know. You already know basically what is an index K n handle. It's this guy right here, and here's sort of his anatomy and all of his words. And let me re-emphasize for you that when you think about an index K handle, what you should really be thinking about is a K cell. We've just thickened it up in the complementary direction so that what we built at the end of the day is a manifold, but you should really think K handle, K cell. Okay, so you already know that, and Aru also told you that all smooth compact four manifolds admit a handle decomposition. Great, so this is a sensible way of studying smooth manifolds. She also told you that you can arrange that your handles come in increasing order of index, so we'll take that, and that you can take your zero handle to be unique, which is convenient. And maybe the final thing that I'll sort of declare or remind us right now is that Aru, I think she didn't prove, but assigned as an exercise that I want to emphasize, I think it's a good one, is that if you modify an attaching sphere, so the way you're gluing a handle onto something, if you modify that attaching sphere by an isotopy, then that doesn't change the manifold that you're building. Okay, so those are our starting points. And now what I'm going to talk about for the rest of the lecture is how do we very explicitly work with handle decompositions of four manifolds. So the game plan is to talk a little bit about how we work with handles of each index. I'll go through them. And once I finish with that, I'll talk about canceling handles, which is a very important idea for the rest of my lecture series and in general. And once we have that, we'll set up some new notation for one handles. Okay, cool. Let's go. I promise to show less on the slides and speak a little less quickly than I did on that one. So great. So I want to start off by talking about zero handles. A zero handle is just a D0, a point cross D4. So there's almost nothing to see here, folks. A zero handle is just a B4. And maybe it's worth pointing out that its boundary is S3. And we only have to take one of them, and they come first. And there's really not too much to say, except I want to make one sort of comment before I move on from zero handles, which is that we think about our handle diagrams, which are the pictures we actually draw when we're trying to describe a handle decomposition of a four manifold. We think about handle diagrams as living in the boundary of our zero handle, aka S3. So when, for the rest of the talk, I draw, well, in general, when we want to think about an index something handle, we can't draw an entire picture of that. The only thing we really know how to draw is in 3 dimensions. So when we draw a handle diagram, what we're really thinking about is drawing a picture of this S3 and then any attaching data of our other handles that might hit this S3. So when we draw these pictures, you should sort of think of the ambient space as a picture as being this S3, and below it, you can't picture that, but whatever, below it is the 4 ball. And to the outside or above that S3, that's where all of our handles live. And we're just going to record the attaching data in here. Okay, great. So what's a one handle? A one handle, again, the important direction is just the first one. So we're really thinking of a one handle as basically just being an arc, a D1 attached to a 4 ball, say. But as usual, it's been thickened up. So we're really looking at something like that. And the thickening in this case is going to be a D3. So when we want to draw a handle diagram, or when I want to tell you, hey, why don't you attach a one handle to the 4 ball, the picture you're going to try to draw is in S3. It's in this boundary of the 4 ball. So the only thing we can really draw of this one handle is the part of the one handle that hits this S3. And what is that? Well, it's just like the feet of the one handle right here. So what are these feet? Let me move that label out of here. Well, okay, these feet are the boundary of our sort of important direction. And then of course they're thickened up. So if you want to draw a handle diagram of a 4 ball union to one handle, what you should draw is sort of nothing for the 4 ball. And then you want to draw these feet. And what are they? That's an S0 cross D3. So that's 2 3 balls. So this is what a handle diagram of a one handle attached to the 4 ball might look like. We just see in that boundary S3, the feet of the one handle, like this. And what we're thinking when we see this is, well, what's in the picture? There is a tube to the outside, which runs between these two V3. Okay. There's another perspective that I sometimes like to use to think about one handles that I think is worth pointing out. So let me say an alternate perspective. So this is our sort of standard schematic of a 4 ball with a one handle, this schematic picture right here. But I claim we can see from this schematic that the 4 ball with a one handle stuck to it is also diffeomorphic to a space that looks a little bit demonic. Let me draw it and then you'll see that it's a little demonic, at least like sideways. Okay, I claim that this manifold up here, our standard schematic for a 4 ball with a one handle is diffeomorphic to this thing right here. And what I've done to write down this diffeomorphism is I've sort of shrunk the D1 of the one handle, right? So now my one handle appears very, very short. And if I shrunk it all the way, in fact, then what I really would have here is just the 4 ball with some kind of quotient taken. And I sometimes find that to be a helpful perspective. So let me write that down over here. When somebody draws you a handle diagram for a one handle like this, you can think that there's a tube running between them, or you could think that what we're doing here is we're taking B3 and then B4, and then we're quotienting out, right? This was our B4 here. And we're quotienting out by some map, which identifies the BI, the two B3s. And in fact, we have a favorite one that we use all the time. We're often using a quotient map that sort of reflects across this axis. So, if you had something like going for a walk in your 4 manifold and it ran into that ball there, it would pop out over here and keep going. Okay. I want to make another observation about one handles, which is what is the total space you get after attaching a one handle to the four ball? And I claim that that space is a pretty simple one. It should be S1 times D3. So let me try to prove that. We're going to start as usual with our zero handle, but our zero handle is going to be this box here. And it's a box for today because I've parameterized our zero handle. You know, what's a zero handle? It's just a B4. So I can parameterize it if I want to, which I do. I'm going to parameterize it so that this is a D1 and maybe this is a D3. Okay, so let me make that a little bigger. So think about your zero handle like that. And now we need to attach a one handle to it. So how do we attach a one handle? Well, we need to specify where the feet are going to go. So that's an S0 times D3 as above. And while there's a really nice S0 times D3 in this parameterized space, it's sort of these two D3s right here. So attach your three handle to the four ball so that those are its feet. So what are we going to see? We're going to see our D1s going in this direction, and the thickness D3 is like this. Okay, and now I claim we're supposed to just be able to look at this picture and decide that this is S1 times D3, right? So what have we done here? This D1 factor of my zero handle is glued up with the D1 from my one handle. This forms an S1 and it's D3 fat. A corollary of the claim is that, well, now we know what the boundary of the four ball union a one handle is. It's just going to be the boundary of S1 times D3, which is going to be an S1 times S2. That's a fact that we'll actually prove again and use a bit more later in the talk, but I thought it's sort of nice to point out at this point. So that's actually basically everything I want to say about one handles right now. And it seems that nobody has any questions. So very good. We get to talk about two handles now. It's hard to talk to no audience. Okay, so what's a two handle? Here's a description here. It's, we're thinking about it as essentially being a two cell, a D2. It's just thickened up. And we'll recycle our old schematic. So it turns out to be a really useful one. So if we attach a single two handle to the four ball, then what we should see is, well, we want to attach a D2 and thicken it up in two more directions. Okay, I know this is the same picture, but it has value in both settings, I promise. So if I want to draw now a handle diagram for attaching a two handle to the four ball, now remember my handle diagram, it just records what parts of my handles intersect the boundary of the four ball. So again, well, that's just going to be sort of these feet here. But what are these feet for this index? Well, okay, it's going to be the boundary of the important factor. So the boundary of a D2 cross an S1. So in other words, S1 times, oops, sorry, that shouldn't be S1, that should be D2. It's the boundary of the important factor cross the thickening. Great. So the attaching region in this case is an S1 times D2. So to specify a two handle, what you really need to specify is a homeomorphism phi from this attaching region, which is an S1 times D2 into, well, the boundary of whatever space you're trying to attach your two handle to. In our case, that's just S3. All right, so that's what we're going to try to write down when we try to write down the attaching of a two handle. And to do that, let me tell you a fact. This isn't too hard to prove. You could do it if you want to as a sort of advanced exercise. Let me just take the statement for now. And the statement is that specifying a homeomorphism from a solid torus into S3 is the same as specifying what your homeomorphism is going to do to S1 cross 0 and what your homeomorphism is going to do to S1 cross some other point. And we'll find it convenient in this talk to take this other point to be in the boundary of, the second D2 factor of the solid torus. Well, the only D2 factor of the solid torus. Okay, so if you want to specify a two-handle, what you have to specify for me, in fact, is just these two curves in S3. One of them is the image of S1 times 0. So that's the core of the solid torus. You have to tell me where the core of the solid torus is going to land. And we generally think of that as being, you have to tell me like what knot this solid torus is landing onto. But it's not enough to just tell me the knot. You also need to tell me where the image of this other curve is going to be. And the image of this other curve, which in the solid torus, this is just some push off of the core. So you're just telling me where does some push off of the core land. This is called the framing. All right, let me give an example of what this looks like in practice. So you might decide that you want to take your knot to be the figure 8 knot, which I can't necessarily reliably draw. Oh, that's really a disaster. There we go. So maybe that's your knot. And now what's your framing? It's just, the knot's the image of the core of the solid torus. The framing is just the image of some push off of it. So this is going to be some, so our framing is going to be some push off of our knot. And maybe, I don't know, maybe it's this one for now. Okay, so that's an example. That's what a two-handle, that's what a handle decomposition of the 4-ball union a two-handle should look like. And if you're ever doing handle calculus and you get a little confused about framings, I strongly recommend just returning to working with diagrams where you really draw both K and the framing curve out completely explicitly, because this is cumbersome notation, but it's also very, it will make some things clear that sometimes are a little tricky. I suppose you'll see what I mean by that later in your life when you have gotten confused by framings a bit more. Okay, but that's a bit of an aside. What I really want to make as a remark is that these two curves, K and the framing, they have this really special property in the manifold we built, the ball union, the two-handle, which is that they both bound disks. And where does this live? They live in the two-handle. Okay, and why is that? Well, where did we get this solid torus, which we're mapping into S3? We got it from being the feet of this two-handle. And every S1 times a point in the feet of this two-handle bounds a disk, like S1 times 0 bounds the core disk, right? So in particular, K bounds the core, and our framing curve bounds, I don't know what, some push off. Of the core. And maybe one more remark, since we chose to use not just any sort of push off of the core of the solid torus, but one where we've pushed all the way into the boundary of the solid torus, then the push off of the core that the framing bounds, it actually lives in the boundary of the two-handle. So my remark can even be upgraded a little bit. I sort of said here that these curves K and the framing, they end up bounding disks in the two-handle, but the framing even has this even better property that the framing is bounding a disk in the boundary of our manifold, which is something we'll use a bit later. Okay, so that's how you specify a two-handle. You have to specify the knot where you're sort of going to send the solid torus, and you have to specify a framing. You have to specify where you want to send a push off of the core. And a fully sort of correct way to write this down every time is to actually draw that push off. But this notation is a little bit cumbersome. So we have a way to get out of having to draw this gold curve every time. And here's what it is. You want to recall that knots in S3 have a preferred meridian and something that's called the Cipher Longitude. So here you draw this picture quickly. So the meridian is just the curve in the boundary of the tubular neighborhood of the knot that bounds the disk in the tubular neighborhood of the knot. And the preferred longitude, also called the Cipher longitude, this is some curve in the boundary of the tubular neighborhood of the knot that has the following properties. So for one, it has to intersect the meridian in a point. And for two, the homology class of this curve has to be 0 in the homology of the knot complement. And if you've never seen this before, it won't be obvious that this Cipher longitude exists or is unique. You should try to convince yourself of that. And even if you have seen the Cipher longitude before, I want you to try to convince yourself of something else. So exercise. The Cipher longitude, so its definition is this kind of algebraic thing, but you can spot it in any diagram of your knot. It's always going to be the blackboard longitude, which is the longitude you get by, in fact, it happens to be the one I drew in this picture, the longitude you get by just following the knot along and don't do any twists in the diagram, minus some number of copies of the meridian, and the number of copies you should use is W is the rise. Okay, so this box here was to remind us that knots come with a preferred longitude and meridian, these sort of special curves that already have names in the boundary of their tubular neighborhoods. So what are we in the market for? We're in the market for an easier way to record when we want to attach a two-handle to the four ball. And well, what we're going to do is write down the gold curve. So you always have to specify your knot. You don't always have to draw a picture of it, I guess. That's still not the figure eight knot. But you always have to specify your knot. And then instead of writing down the gold curve, you'll just write down what is the gold curve, at least, or what linear combination of these two guys in H1 of the boundary of the tubular neighborhood of the knot, what linear combination of these guys gives the gold curve. So in this case, our gold curve was the Cipher longitude, it looks like +2 meridians. Okay, but since our gold curve, since it is a push off of our knot, it's always going to just go once around our knot sort of longitudinally. Like we'll always just see one copy of the Cipher longitude here. So we actually don't even bother recording this entire thing. We just record the integer coefficient on the meridians. So we'd really just record 2. So in practice, when people want to say, hey, why don't you run along and attach a two-handle to the four ball for me, the instructions they would give you have a tendency to look like this. they draw some knot or link, and next to each curve, they write down an integer. And the integer is encoding this framing here, in this way. Cool. So there's a couple more things I want to tell you about TwoHandles. What we just said was really just a whole slide on how should you describe to me some two-handle attachment that you want to do. Next, I want to talk about what happens to the boundary of a manifold when you attach a two-handle to it. Though I guess really what I'll do is I'll just give an example. What happens to what is the boundary of the 4-ball with a single two-handle stuck to it, as we saw before. And this is not that hard to write down, even just from looking at the schematic. I mean, when I look at the schematic here and I ask, like, all right, what's the boundary of that space? I mean, what I see is that there's a black bit and there's a green bit. And that is correct. That's but we can be a little more precise about what those are. So what is this black stuff here? It used to be at S3 before we stuck the two-handle along. So what's going to remain into the boundary of this manifold is the parts of S3 that didn't get the two-handle stuck to them. So that's going to exactly be the complement of our knot, right? Everything that didn't get a two-handle stuck to it. And what are the green bits? Well, I guess what we're seeing here is we're seeing the boundary of the thickening direction crossed with the D2 that we actually care about here. So the boundary of the 4-ball with a two-handle stuck to it is in fact a knot complement union a solid torus. And that's going to be a familiar sort of object for a lot of people. That's some kind of Dane surgery on our knot. But I want to comment that we can actually see what kind of Dane surgery it is, because we understand, I didn't write it down, well, we understand the way these two spaces are glued together, right? It's whatever gluing happens here. And we just wrote that down on the last slide. And what we saw is that S1 cross that black point is getting sent to our framing curve. And remember, we observed that this S1 times a point, that bounds this disk in the boundary of our manifold. So what we see is that this framing curve for our knot, that bounds a disk in this space. So what does that tell us? It says that we're sending the meridian of this solid torus onto our framing curve. So the Dane surgery that I've done here is exactly the same. This sort of has the same framing as the framing I used to attach the handle. Okay. A word about the algebraic topology of two-handles. So the first thing that's not at all hard to check, and I won't go through this carefully, is that two-handles, they're going to give you your generators of H2. Okay, but they also tell us more than that. They tell us about the intersection format, and Andras told you how. In fact, he gave this as an exercise, and his exercise was more substantial than what I've quoted him as saying here. But what he told you is that if you take some homology class and the two-handle H that sort of provides the generator for it, then the framing on that two-handle is the same thing as the self-intersection of that homology class. So I know Andras gave you this for homework, which maybe you're good students and you've already done, but I'm going to do this part of it for you, because I think this can be checked really explicitly and geometrically, but it's not often written down. So I wanted to take the time to do that now. Okay, so first, let's make sure we know what we're trying to compute here. What is the self-intersection number of a homology class in a four manifold? Well, it can be written down as the size of the intersection of surfaces, maybe sigma and gamma, where sigma and gamma, their homology classes, both represent little sigma. Okay, so to make this computation, what we're going to try to do is just, for some two-handle, we're going to try to write down two surfaces, sigma and gamma, that both represent the homology class coming from that handle, and then we're going to look at their intersection and try to count how many points are in it. So here we go. Let me start off by building a surface sigma. So and I'm just going to prove this again in the case where we just have two-handle attached to the four ball for simplicity. So, all right, here's a picture of our space, as usual. I claim there's a couple of kind of natural surfaces in here. One of them is the core of the two-handle. So that's a nice disk. Its boundary is the knot K. And we also have a ciphered surface for K, which maybe I'll call delta here. Okay, so delta is not properly embedded in this four-ball union two-handle. That's fine. Like, we just need a cycle to get a generator of homology. But it'll turn out to be convenient to push delta in and get something embedded. So let's clean this up a little bit. We'll take the core again, and then we'll take just some trivial push in of that ciphered surface delta. We'll call it delta prime. So we're not moving the boundary, and we're just pushing everything else into the four ball a little bit. And the union of these two surfaces here is going to be our surface sigma. All right, and that certainly gives a generator of H2 of this manifold. So that was easy. That was sigma. Now we just need one more surface generating this homology class. So let's try again. We'll try to do a very similar thing. So here's our space again. So instead of taking the core, let's take, I don't know, some C prime. It's just a push off of the core, something like what we did before. And instead of taking delta, we'll take, oh gosh, delta prime, which is again some epsilon push off of delta. But I want to emphasize that I'm doing this push off in S3. So, right, in S3, like if what I had before was my knot K and the ciphered surface delta running off from it, then this surface delta prime, it has boundary, epsilon K, and it runs parallel to. Okay, fine. That's some surface very similar to what we did before, and just like before, it'll be convenient to instead push delta prime into the four ball. So we'll call, oops, sorry, that shouldn't have been called delta prime because that thing's called delta prime. Let's call this delta bar. Sorry about that. And now this here will be delta bar prime. That's delta bar, which has been pushed in. Okay, and here's. All right, so what am I trying to do here? Why am I drawing C prime and delta prime? I'm supposed to be writing down another surface that generates homology of this manifold, generates H2. And you might think I'm being like a little thick in how I've drawn this schematic. Like I've drawn this in such a way so that the boundary of C prime like doesn't look like it lines up with the boundary of delta bar prime. But in fact, that's deliberate. These boundaries, they don't have to match. Like let's have a look at what these boundaries actually are, because that's not the delete button. Because we can, right? Because the boundaries that we're interested in, where do they live? They live in the tubular neighborhood of our knot K. So that's a space in a 3 manifold. So we can actually just look. So if this is a tubular neighborhood of K, and maybe here's K, here in the middle of it, then, well, what's the boundary of delta bar prime? I claim it's going to be a curve just like this. Right, it's very close to K because we used a small push off. And I also claim it has to Cipher frame K because, well, exactly because we pushed, we got delta bar by pushing a ciphered surface in S3. Great, so that's what the boundary of delta bar prime looks like. What does the boundary of C prime look like? Well, C prime is this push off of the core, and it may as well have been the one we used to compute the framing. So the boundary of C prime is exactly our framing curve, which is some interesting thing that goes around the knot longitudinally once, but may have many meridians. All right, and so these two curves, they don't coincide in this tubular neighborhood, but we can take a little surface in there that lines them up, that gets us a closed surface. And so let's do that. We'll just take this annulus here, running between, oops, that's too big. C prime and boundary C prime and boundary delta prime. Okay. So with all of that, which might seem like a little bit much, we've defined a second surface gamma that generates homology. So gamma is going to be C prime union this annulus A union delta bar prime. So this is our annulus. Okay. So now if I want to compute the self-intersection of this homology class, all I have to do is take my surface sigma and my surface gamma and intersect them. So let's draw sigma in this bottom picture here. I claim it's just this guy, right? A copy of the core and a copy of this pushed in ciphered surface. And what you want to observe is that gamma intersects sigma. Well, it's the same thing as A intersects sigma, because my surfaces, they don't intersect out here in the handle because we just have the core and a push off of the core. And they don't intersect in here in the 4-ball because we just took 2 ciphered surfaces and pushed them both in. And if we were careful, we use the same push-in function, so they don't intersect in here. So the only places sigma and gamma can intersect is in the tubular neighborhood of the knot. And now in the tubular neighborhood of the knot, we know exactly what gamma looks like. It looks like our annulus A. And we also know exactly what sigma looks like. Sigma runs through this S3. Oh gosh, that was not the highlighter. Transversely. So we only see sigma running through the neighborhood of the knot in exactly the knot itself, in K. So A intersect sigma is exactly just going to be A intersect K. And I'll leave it for you to finish off, proving that the intersection of that annulus with the knot, the core of the solid torus, is precisely the framing. as usual, no questions. So there's one more thing I want to tell you about two handles, which is that we can slide them over each other. Let me say what that means. But to do that, let me first remind you the sort of principal tenet of handle slides, which is just this fact that you already know that a root assigned for an exercise, which is that doing an isotopy of your attaching spheres doesn't change your manifold. So this is going to seem really pedantic, but bear with me. Like if I tell you to build this manifold, but you're feeling like very like doing your own thing. So what you decide to do is instead build this manifold. That's fine. We haven't actually built different spaces. That seems silly, but we're going to come back to it later. So what this means a little more generally, if you have what this observation about the fact that you can isotope attaching spheres without changing the space you've built means a little more generally, is that, if you're building a space, and this is just some schematic here. If you're building a space, maybe you start with a 0 handle and you attach some first handle. Maybe these are both 2 handles. So that's a first 2 handle, and then you attach a second 2 handle. You're allowed to modify the attaching sphere of that second 2 handle by an isotopy. So in particular, you can move it around however you like in the boundary of whatever was there before. And the boundary of whatever was there before is, it's not just this S3, it's actually this S3 that's been modified by doing this handle attachment. And so the sort of toy picture you always see people draw is that this space is the same thing as this space. You're allowed to sort of take the feet of the blue handle and push them across the green handle if you want to. So that's the sort of schematic of what is a handle slide. So it's just an isotopy, but where you recognize that any lower index handles, they might have contributed some interesting topology for the boundary, and we can use that topology to do our isotopy. Let me show you what this might look like in practice for a pair of 2 handles attached to a 4 ball. So let's suppose the first 2 handle I attached was attached along a trefoil, and maybe it's 3-framed. And then the second handle I attached, like, I don't know, I'm not feeling very inspired. I just attach another 3-framed trefoil, and this is the manifold I'm building. Okay, so since the blue handle went on second, I'm allowed to isotope it around in the boundary of the manifold we built with the green handle. What does that mean? Like what kind of isotopies are permissible here? What can I use that green 3-framed curve for? Well, remember, what does the 3-framing really mean? Like, it really means that we're attaching a 2 handle so that this copy of the green curve bounds a disk. And in fact, remember, it bounds a disk, in our 2 handle, but in fact, in the boundary of our 2 handle, and in fact, in the boundary of the manifold we get by just attaching this green handle. So let me put that aside for a second and draw your attention back up here to this stupid example. If I was being really pedantic and I wanted to explain to you, why these 2 manifolds up here or if I wanted to explain to you why this was an isotopy of that attaching sphere, what I'd probably point out is like, well, look, like there's a disk in my ambient space right here. And so what I can do is I can take this little part of my attaching sphere that's kind of close to the boundary of the disk, and I can swing it, instead of running like near the boundary on this side, I can swing it across the disk so that it runs this way. And that's what we've done. And so what's a 2 handle slide? Well, you just come back down here and you say, aha, this curve right here, it bounds a disk in the boundary of this handle attachment. So what I'm allowed to do is take my 3 handle and, okay, first just like isotope it with a little finger move like this. And then sweep this little arc of of my blue attaching sphere across that disk that I know lives in the boundary of this green two handle. And what we see when we do that is that the blue handle is going to go the other way around this disk. Okay, so that's a handle slide. It looks very violent, but really it's just an isotopy of some two handle that we're thinking of as being attached after some other two handle. So let me make a comment about it. You should be unhappy about this now. This 3, what was it? It was just this notation that was helping us encode these golden framing curves. But it depended on that Cipher longitude for our knot. And when we did this handle slide, the blue curve, it changed knot types. And you can check that 3 sort of no longer correctly represents the way we should want this blue handle to be framed. And the way you should decide how you want this blue handle to be framed is you should go back to the golden standard where you actually just draw in your framing curve. So if our framing curve from before went something like this, then when we do this handle slide, our framing curve, it better come along. So it's going to go somewhere like this. Follow along. And this is some honest new, the real right one framing curve for the new blue knot that we have here. So when you do handle slides, the sort of formally correct thing to do is convert back into sort of honest framing notation and slide your framings along as well. Let me remove this because the picture is a disaster. But in practice, we still don't actually want to have to draw these framing curves in all the time. So let me give you an exercise which will teach you how to get out of drawing these framing curves in practice in general. And so the exercise is, how should integer framings change under slides? Okay. So that's everything I want to tell you about two handles. Great. There's 2 more types of handles you might attach to a 4 manifold. They're 3 and 4 handles, but Andras already told us this sort of very important fact about them, which is that if you're building a closed 4 manifold, then it doesn't actually matter how you attach your 3 and 4 handles. You're always going to get the same 4 manifold. And we're going to take that as a great excuse to ignore 3 and 4 handles for now. The other folks are mostly building closed manifolds, and I don't think I'm going to need 3 handles in my section, so we're not going to. Great. So now that we've met handles of every type, there's really one thing I want to tell you about how they interact. It's that they can cancel, and once we know that, we'll use that to give us a new way to think about one handles. So let me start off by telling you about canceling handles. And the lemma statement for canceling handles is here. So what it says is that if you have a pair of handles, a 1 handle H1 and a 2 handle H2, and they're attached to some 4 manifold X in such a way that the attaching sphere of the 2 handle intersects the belt sphere of the 1 handle in just a single point, then the space you get from starting with X, attaching both of your handles, is just diffeomorphic to not having done anything to your starting space X. And there's this really standard picture everybody always draws to illustrate this, this lemma, and it's this one. So this is a 3-dimensional picture. So what we see here is we have this 3-dimensional 1 handle attached to some space below. And we're being told, why don't you attach a 2 handle here with attaching sphere like this? So a 2 handle, remember, it should mostly be thought of as a disk. So a 3-dimensional 2 handle, you could think of that as like a can of soup disk, but it's kind of tall. And when you glue your can of soup in so that this is the attaching sphere, what you're really doing is just taking this can of soup and wedging it into this tunnel. Okay, and then we see just from the picture that our space is, it's just X with this bump on it, which it's easy to prove. It's just diffeomorphic to X. So that's supposed to be why this lemma is kind of obvious. But I don't find this tremendously convincing, because even in 3 dimensions, I don't think this lemma is super obvious. Like, let's look at this example over here. So this is an example where we start with a 3-manifold X, which is a solid torus, and we attach a 1 handle. And I'm telling you to attach a 2 handle along this blue curve. And this blue curve has its attaching sphere running once over the handle. So it hits the belt sphere 1 time. So this satisfies the lemma. So when I stick my soup can on here so that its label goes along this blue curve, I'm supposed to get the solid torus back. And that's not at all clear to me from this picture. So I wanted to say something about how you prove this lemma, because I don't think it's so clear. So proof sketch. Well, first, let me tell you the proof slogan. Okay, the proof slogan is we're going to use the 2 handle as a winch to topple the 1 handle. All right, so what does that mean? If I look at the manifold X union my 1 handle, union my 2 handle, I'm not going to draw a picture of it, but I know that somewhere in there is my 2 handle, which basically looks like a D2. Okay, it's been thickened up, but I'm suppressing that thickening from the picture. All right, so I have my 2 handle somewhere in this space, and I know a little bit about it. I know that its boundary has sort of 1 arc in the 1 handle, and then the entire rest of the boundary is in X, right? Because the attaching sphere of my 2 handle only runs over the 1 handle that 1 time. So I don't have to see more than 1 green interval. Okay, so my 2 handle is in here somewhere like this. And so what I can do is I can use this 2 handle to write down a diffeomorphism of this space. And the way I'm going to describe the diffeomorphism is I'm going to contract my D2, and I want to do this contraction like cross D2, so in the thickening direction as well, but we're just not going to draw that. And I'm contracting my disk so that, oops, wrong thing, so that the part of the boundary that's in X is getting very close to the part of the boundary that's in the 1 handle. Okay. And in fact, we can actually just flatten that disk down all the way, oops, to an arc. And what we see when we get all the way down here is, we started off with X union a 1 handle and union a 2 handle, and now we really compressed the 2 handle right down to nothing. So this space now kind of looks like its total space is just X and our 1 handle. But you need to be really careful here. We've changed the way that our 1 handle touches X, right? Because we've taken these points, which used to be in X and not in the 1 handle, and we've made them touch the 1 handle here. So we've changed the gluing. And what's a 1 handle once you modify its gluing? Like handles are all just balls. The thing that makes something a K handle as opposed to a 1 handle is what's its attaching information, and we've messed with the attaching information. So I should really not even describe this as a 1 handle anymore. I should really just describe this as X union a 4 ball. And now you have to check, okay, but how are they glued together now? And I claim, I'm not going to check this carefully right now. I claim that they're now stuck together along a B3. I think a good test case for that is to look at what you think is happening up in this example. So if we had stuck our two handle here and then we had sort of compressed it, what would have happened? We would have taken this arc, this sort of arch of the one handle, and we would have dragged it over until it sort of lied flat on its side, running along this complicated blue curve. And so then you just have to ask yourself, all right, but now how does all the green stuff touch X once I do that? And up here, the answer will be in a D2. Okay, but then what is this space? X with a 4 ball stuck to it along B3. Well, that's just X boundary sum B4, and that's just X again. So that's how I think about canceling handles. Canceling handles are going to be very, very important for sort of in their own right in the final next 4 lectures of my course, and they come up a lot in the literature on their own, but they have this other application, which is they let us give a new notation for one handles. So let me talk to you a little bit about this, and let me first just make a sort of silly observation that follows as a corollary of this handle cancellation lemma we just proved. So the silly observation is that if you start with any 4 manifold and you have a one handle attached to it, that's the same thing. This is going to be really tautological. That's the same thing as same manifold, same one handle. And then you attach a canceling 2 handle, and then you just remove that exact same canceling 2 handle. So this diffeomorphism should be like the do nothing diffeomorphism. Put something on, cut it back off. And now we can apply the lemma from last time to say that, but X union a one handle union a canceling 2 handle, that's just X again. So what we observe is that, X union a one handle is the same thing as X remove, where you need to remove some canceling 2 handle. Okay, so if you don't want to think about one handles, what you could do instead is you could think about removing canceling 2 handles. But to do that, you'd probably need to know, like, what does this really mean? So I want to try to unpack that a little. How do you remove a canceling 2 handle? And the first thing I want to claim is just something about how you remove any handle. And that claim is that if you take a manifold that has a K handle attached, and then you cut out a neighborhood of the co-core of that handle, that'll do it. That'll have the effect of sort of not having attached your handle at all. And what's the proof of this? Well, okay, you start with X, which is sort of, maybe down here. And you have your K handle stuck to it like this. And now what are we going to do? We're going to remove the co-core. What's the co-core disk look like? Remember, it's this. So what does it look like when we remove the co-core? Well, okay, we still see X down here. And then what remains of my handle is probably looks like this. Okay, and so what is this? Well, it's still thick in exactly the same way. So it's still something cross dn minus k. And what is that something? Well, each of these dk that we had before, they got a neighborhood of the center cut out of them when we cut out the co-core. So this dk has turned into s k minus 1 cross I, right? It's this is sort of annulus that comes from the boundary of dk towards the middle, but doesn't quite get there. Okay, so this space was X union the K handle, and this space is, well, that space with the co-core removed. And this space here, I claim we know how to write down a diffeomorphism, simplifying it. What we're going to do is we're going to contract this I factor. And what's that going to do? It's going to take this SK minus 1 cross I that used to come up here close to the co-core and cause it to not go very far at all. What we see is something like this. And it's not so hard to finish this off and show that this is just diffeomorphic to X. Okay, so what we observed at the top of the page is that if you want to add a one handle, what you could do instead is you could remove a canceling two handle. And what we just learned in the claim is how to remove a handle. You remove a handle by cutting out a neighborhood of its co-core. So now what we're interested in doing is learning how to remove co-cores of canceling two handles. To do that, we just have to recognize like what kinds of things are co-cores of canceling two handles. And I claim that we can spot those. Co-cores of canceling two handles are our boundary parallel disks, and they're always going to be boundary parallel D n minus 2 because they're the co-core of a two handle. All right, so let me try to show you why this is true with an example. And the example will be three-dimensional. So here's B3. Maybe it has a one handle stuck to it. And then a canceling two handle stuck to that. All right, so where's the co-core of the canceling two handle here? Well, it's sort of like this D3 minus 2, so D1 in this dimension right here. So this is the co-core. All right. So if we're going to try to remove this blue two handle, what we're going to do is cut out the co-core. Very good, that makes sense in this picture, and that'll sort of give us back our one handle. But I want to find some way to recognize this co-core without having to know like where were the one and two handles that it came from. So first let me observe that this co-core, it can be isotoped around, and in particular it could be isotoped around until it was like, I don't know, right here. Right. So that's a perfectly good co-core as well. I just sort of dragged it off to the side. And now from this picture where we've kind of dragged our co-core of our two handle off to the boundary of the two handle, what it's not so hard to see is that, you know, indeed this co-core disk is boundary parallel. And how are you going to get it out to the boundary of this B3 here? You're going to push it across that D2, which is the thickness of your one handle. So I'm not claiming to completely write this down in full generality or in all dimensions, but this is how you would show that a D2 co-core of a two handle that's canceling in a four manifold is boundary parallel. Is you'd still say I can use the thickness of my one handle as that disk that pushes it out to the boundary. Okay, so what that means for us in practice is that if you don't know where that one and two handle came from, if I just give you this sort of total space and say, hey, can you like run along and cut out a co-core of a canceling two handle for me? Well, in fact, you do know how to do that. What you need to do is find some boundary parallel D n minus 2. And the way I like to do that is I just take some D n minus 2 that's actually in the boundary. Sometimes I think of this as being like the shadow of the co-core. We see it over here too. It's this gray curve that I pushed out. And you know, in this picture here, we'll just push it in and remove a neighborhood there. Okay. I drew these shadow disks for a reason. I want to make one observation here, which is that if I had some additional handles that were maybe trying to run over this one handle, then they would hit the shadow of the co-core. And we'll use that in just a second. But observation about additional two handles aside, what we just showed here is that if for whatever reason you don't want to attach one handles, you can instead remove boundary parallel dn minus 2s. And the notation we use for that is, well, sort of as I said before, what I like to do is find a dn minus 2. So in 4 dimensions, that's going to be a d2. So I like to find an honest dn minus 2 in my actual boundary. So here's an honest dn minus 2 in S3. And then push it in and cut it out. And of course, I can't draw that for you. And the notation we use is we draw an unknot with a dot on it. And I suppose a final comment is as I said up here, if there had been additional additional 2 handles running over this one handle, well, they would hit this shadow disk. Well, what that sort of indicates for us here is that any 2 handles that are sort of running over the one handle that this came from, what they're going to need to do is run through this disk and so run through the unknot that we drew. Okay, I'm aware that I'm a little bit over time, so let me just make a couple of final comments. In fact, I'll really just make one. This top bullet point here is the most important. So let me comment that we can again look at the boundary of our one handles in this new way and make sense of that space. So how should you think about this new way? How should you draw schematically this new way of describing a one handle? Well, sort of as before, we start with the 4 ball. But now what we're going to do is we're going to remove this disk. And this disk is boundary parallel, so its boundary, as we just saw, has to be an unknot. And so what are we really doing here? We're taking a neighborhood of this disk and we're cutting it out. So this is a schematic picture of sort of this new way of thinking about one handles. And if I'm interested in the boundary of this, well, we can do exactly what we did before. We can say, well, looking at the schematic, I can see that this boundary has to have a black bit and a blue bit. And in fact, exactly as before, what's the black bit? It's all the parts of the boundary of the 4 ball that didn't come too close to the unknot. So the black bit is S3 minus a neighborhood of U. And what's the purple bit? Well, what did we cut out? We cut out this neighborhood of a D2. So the sort of boundary we left behind is this S1 bundle over D2, or S1 times D2. Okay, so this is going to be some Dane surgery again. And what Dane surgery is it going to be? Well, let me give this to you as an exercise. I claim it's going to be the 0-framed Dane surgery on the unknot. So there's sort of an easy way to do this exercise, which is to compare with the boundary of the one handles that I described much earlier in the talk. The harder way to do this exercise, which I think is really worth doing, if you have a few minutes, is to try to prove that this framing coefficient should be 0 more abstractly, just by looking at this gluing information here. Okay, and there's one remark I want to make to close us off, which is that the boundary of a one handle in our new notation, okay, we just saw it's going to be the 0 surgery on the unknot, the knot in the notation. And that's exactly the same thing as the boundary of the manifold you get by attaching a 0-framed 2 handle to the unknot. So the boundary can't tell whether you added a one handle in this sort of new way of thinking about one handles, where in fact you remove a boundary parallel disk, versus whether you attached a two handle. And that should probably look like a cute little coincidence for now. But this is actually a fact that I'm going to leverage again and again later in this course. Okay, so I'm going to stop there. Thanks so much. I'm excited to take questions in the office hour in a couple of weeks. Yes, very good. Thanks.